We're going to take you to a reliability journey that is going to begin 20 years ago, actually, or even further down. And to me, this is a journey. It never stops. We will have to improve, and we have to rethink the way that we do these things on reliability. It's really a complex thing, and we will talk about that in more detail. But now I would like to present ourselves. So my name is Erik van Opna. I worked at Euroclear. So what is Euroclear? I will explain. I saw this morning that there were a lot of financial, people working in the financial sector, so they probably know, but I will explain that. I am a transformation lead for resilience. I'm a musical enthusiast. I like jazz. I play bass guitar to the horror of my wife. So the funny thing about the basic guitar, I thought it was simple because there were only 4 strings on the bass instead of a guitar, 6 strings, so it should be simpler. That's not the case. If you think that, that's wrong. And the other thing that I did is that, and that's COVID for you, I learned sax, and I annoyed my wife even more because the sax, that makes a lot of noise. So there is no volume button on it, so it's always loud. And I played baritone sax as well, which is also an annoying thing, so voilà. That's me. Would like to introduce my friend Haytham. We went on this journey, since a while. He's the application reliability factory lead. We have a reliability factory, an application factory. We are both jazz fans, but he has this combination with metal. I don't really get this, so metal and jazz. So he likes to play golf a lot, and you are in the perfect country for this, and snowboarding. All right, this proverb, trust. We talked about trust before. Trust is, you have this proverb, this is coming from the Dutch statesman when they actually reduced 150 years ago the constitution of the Netherlands, and they restricted the power of the king. So we keep talking about kings, so maybe that was a good thing. And this person that did this, he had this saying, so trust arrives on foot and leaves on horseback. And in my imagination, and maybe it's a bit weird, but I always see a snail, a snail, very slow. Typically, this is then a snail with asthma, so it's even worse. And it took probably some Dafalgan or paracetamol, or these days Tylenol. It's on the top. So it comes to you, trust. Imagine it very, very slowly. Sometimes it loses the way, so you have to get it there. And then if you screw it up, it disappears. It's all out of the ballpark super quickly, like rocket speed, SpaceX stuff. So you lose it quite rapidly, and it's difficult to get it back. So what does that mean, trust? And trust for us in this context, we have reliability. For us, it's reliability and consistency. We need to be reliable. That means that we need to be there. So whatever it happens, if it's a cyber attack, and if it's just a disaster, we lose a region, we lose an availability zone, we have whatever incident that we have to be reliable. And on top of that, we have to be consistent. That means that we can come back, but our data needs to be consistent. The data needs to be reflecting where we were before, whatever happened before, right? So that's the key here. Now I would like to explain to you what Euroclear actually does. There are a lot of financial people here. So we are a financial market infrastructure, an FMI, for those who know this. And I'm going to take you to a small, very, very rapid crash course on financial, how the backbone actually is working. We talk a lot about the next big thing. So are there somebody can shout out what the next big thing is? NVIDIA, AMD signed a deal with OpenAI. Anybody? What do you think? Nothing? No stock picking people here? No? AMD, cool. So AMD, so let's say that we want to buy an AMD. Somebody is really excited about this deal on OpenAI. Want to buy this the stock from AMD. Needs, of course, to have the money to buy the stock. And if you want to buy the stock, you have to have somebody who actually wants to sell the stock. So, and then you have the play of the pricing, stock exchange, you buy something, and then what happens next? So this is a trading level. You have to go to a broker-dealer. You have to use your online platform or your bank or whatever, but basically there underneath there is a broker-dealer handling your transaction. Next step that we take down, that broker-dealer will go, or both, it can be the same, to what is called a central counterparty, the CCP. They check, and you can compare that if you buy a house. If you buy a house, you will also have the money that you need to provide to buy the house, and of course the fact that you are the owner of the house for the people that sell that. It's the same story here. That's what the CCP does. Check is the securities there, is the money there. And then the final step, and that's where Euroclear operates, that's in the settlement step. That is where you have the finality of the records. That is when you sign the deed buying your house, that is where you can go to court with this. It's sometimes called the book of record or the record of finality. So that is where you can go to court with this money. We have, what we do is called the CSD, so a Central Securities Depository. And in fact, we have 6 of them. And you can say, why do you have 6 of them? Is no one not enough? Well, the landscape in Europe, as you probably know, is very scattered. We have 27 different CSDs. We had at once a big dream that we're going to unify this. The ECB, the European Central Bank, is actually trying to unify that with the T2S and Target 2 and Target 2 security. But nevertheless, we still have a CSD because there are a lot more actions that you need to do to complete the activities that are happening there. Maybe we'll go back one slide. There are a couple of points that I would like to make here. First of all, if you look at this, you see that there are hundreds on the top, you see that there are a lot of transactions, high volume, but the value is very little. And the way that you go down, actually the volume is reducing, but the value in the transaction is actually increasing a lot. And we are talking about billions sometimes, right? So in one transaction or a couple of transactions. The other thing that you have to see in the middle there, you have the trust, the CCP and the CSDs. This is trust basically. Why? Because nobody in the financial world trusts the other guy. So this is not happening. So that's why the CCP is there. And if you follow the news, Euroclear normally is a sort of a covert organization. We are lately in the news, and this has to do with the Russian billions that are stored. You probably see it with the Ukraine war, where they want to take, confiscate some of this money. But then you kill trust. You see, you kill trust, and if you kill trust, this model is basically a bit under pressure at that time. All right. So, what are we talking about? Well, I like to say, because we are going to talk about trillions and billions, and so sometimes it's really confusing to talk about that. And so, how I want to present is that we are running every night in the overnight the GDP of Belgium. The GDP, so that's what all the so Belgium is a small country, I agree. But they run, so what all Belgians together are doing in a year, what they generate as money, GDP. And so we run that 6 times a night through our systems in a value. Of it's not our money, but it's from a value point of view, that's what we do. So that's where you get this 1.6 trillions, and if you divide it by we do about 300 million transactions in a year. So you get that. We have 40 trillion assets under custody. So it means we have once you do the settlement, you have to store it somewhere. And it used to be in bearer notes, so you have physical paper, but now it's all digital. So you have to store that. That is what they call safekeeping. That's one thing. We have 3,800 clients. And then the right-hand side is also important. That is the collateral highway, and we're going to talk about that collateral highway, what that means, because this is actually to fuel the deal or the settlement during the way, and voila. So, what do we do? So, there is no undo. Our data must be perfect in the sense that we cannot just rerun the applications again or the transactions again, because the market is dynamic. The situation changes. Collateral can move. So, this is not happening by itself. So it's not just a database. We have an authoritative record that we have to care about. It's of course trillions of assets, as I explained. We have the settlement. We have an immutability about the records. So these records are final. So we have a huge archiving system so to make sure that if somebody pulls up, like the Lehman Brothers, when we had the financial market crisis that we had in 2008, there were a lot of claims, of course, because the Lehman Brothers fell over. But what you had underneath, you had a lot of collateral, which fuels the deal. So if somebody falls out of that thing, how do you unwind all of this? So that was actually happening on a Friday, and on a Monday morning, you have to open your market again with, the unwinding done. It was a very busy weekend, I can tell you that, in 2008. So that's what it is. And so if collateral management goes bad or south, it has a ripple effect in the whole market. That's basically what you have there. Okay.
So basically, it's clear that for us reliability is really different. For us, we don't particularly. I mean, the problem is not a 99.999 problem. It's global stability, right? It's really anything we do can and will have a domino effect, right? And it could also generate a geopolitical crisis between. So during outages, if they happen, and they do happen, you will end up with a chaos of, okay, so who owns this asset? Who owns the security? So on and so forth. Right? So because we maintain those asset ownership, what we need to do during failures and disaster is not easy, right? So, and at the end of the day, because when we talk about availability or reliability or SLOs or SLAs, it's not only about the service, but it's also about the data. How correct is the data that is available, right? So we are in what we call a reliability trilemma, where we need to be in an absolute consistency manner, right? We need to also be extremely available in what we also call the EBPS, the extreme but plausible scenarios, right? So we need to think about all of these things. Things like a regional failure is one thing, right? But we also try to look at things that could impact during revolutions, wars, nuclear bombs, so on and so forth, right? And lastly, everything we do should be verifiable, right? So the trade-offs that many of our peers that are not in the financial institutions, that typically, I mean, web and social media and Google's, they might not really apply to us, right? So and look, I mean, from a regulator perspective, it's even more important.
Yeah, indeed, because we have heard about LoRa, which explained DORA. LoRa explained DORA. So, but we are actually focusing here on our side. We have the regulator. They look at things. Of course, they have a lot of regulations going on, but specifically on RTO, they mainly focus on the 2-hour RTO from our perspective. And we're going to talk about RPOs because RPOs is actually important for us. It's actually even if it's a bigger trouble for us than the RTO. That's one thing. So as I said today, focusing on security and hardening, I think we have here heard this before. So it's about how do you be compliant with all these rules? How do you check? How do you report this? How do you come back and make sure that? And again, it's about trust. So can they trust you? Yeah. We have, from a regulatory point of view, it's not one framework. We are facing more than 40, what you could call regulations. The most important one is the CPMI IOSCO PFMI 17, which basically says that you have to come back in the service in 2 hours, whatever that happens. Whether it's a ransomware, it's whatever that happens. So that's what we're aiming for. So you could say that you can throw anything, so we have to come back in 2 hours. That's the point. But there are a lot of other things like the Swift CSP. For those who know that, so the ISAI 3402 is something that we are inflicting on ourselves. The French military law, which is the ANSI, so the ANSI with one S and the other ANSI with the two ANSIs, so it's a bit confusing, but there are two of them, and so on, so on. So a lot of these things. DORA itself of course, we are certainly addressing this, but a lot of these DORA regulations were already included in the other ones. So the ones coming from the regulator itself and so on, and the ones that I just listed also have that.
Yeah. So it's DORA and these things, they all also, I mean, even the business, they all talk about speeds, you know, how quickly we can recover, how quickly we can hide failures, right? But again, for us, we need to be reliable in a consistent manner. We need to ensure that since we're not in an EDA world yet, right? Any attempt to lower that RTO and availability service level, it will impact the RPO, because again, when you try to achieve a very aggressive SLO, you also need to ensure that whatever data you are providing to your third parties is correct, and if it's not, it's really a big thing, right? So and when we talk about the recovery point of objective, about how much data we're willing to lose, remember that this data is billions of euros, right? It's not just how many shirts do we have in the inventory, right? It's really billions of euros. So for us, when we talk about the most important thing for us is to have an available state, right? So for us, state is really everything. Now, what do we mean by state in Euroclear?
Exactly. So what do we mean by state? So this is a blast from the past. So 20 years ago in this journey, so there was one thing that really shocked the financial world, of course, the world itself as well, but the 9/11 events, so the 24 years ago in 2001, the Twin Tower incident, there were companies that actually had their backup center in the other tower, so Cantor Fitzgerald, you have to look it up, so it's a fascinating story, by the way. And how they recovered, very interesting. So this shocked as well our management. So we had at that time, 6 data centers. There were 3 twin data centers, you would call that. So it's a metropolitan setup, 2 data centers in cities, different cities, capitals in Europe. And then, of course, we didn't have a regional disaster solution. So what we came up with is we introduced C here in this drawing, which is basically A and B are synchronous data centers like we had before, and the C is the asynchronous data center. So why do we want to do that? Of course, to protect against this situation, but also we did something else because we had some trouble of having all of these different ledgers, and you see there all these things in the red, settlement, reporting, cash, and so on. We were also divergent from typically a mainframe environment to an open systems environment. And so we bought a lot of companies. Of course, we bought a lot of companies, and they all had a different stack. That was funny. So if you want to look at Oracles and SQLs and Postgres and whatever, we have more or less everything. So at that time, certainly. So we tried to gradually move that off, but at that time we had this issue. So we had the issue of being atomic. What it doesn't mean to be atomic. You have to be on the same data set. You have to assure that we have heard things about how the system can lie to you, that you have to have double write buffers, you have disk systems that actually have buffers that you are not aware, you have to disable caches, of course, impacting performance. So that was a problem for us. So that's where we came up with, so we didn't want to have fractured states, even if you work asynchronously, because that's where synchronously is relatively easy, asynchronously is another story. Point-in-time consistency, we have to come back on that trust point that I mentioned, the reliability and consistency needs to be there. So if we lose data, because if we replicate everything everywhere, if you lose data or it's corrupted everywhere, quickly, honestly. So we're very good in corrupting data everywhere. Once it's corrupted everywhere. So we built a one-of-a-kind solution. It's actually engineered with Euroclear. We started this so I'm talking here 20 years ago, so we engineered that at Euroclear. That solution is basically providing a single consistent bounded context between mainframe and open systems. That's what we built. So that worked very well. It grew massively, but it doesn't scale in the new world. If you want to go to cloud, of course, this is bespoke legacy stuff that we built. So that you don't find this thing in cloud. The other thing that we had, these specific consistency groups exist, of course. We are not the only one. But this type of a consistency group, I think we can safely say that we are practically the only one in the world that's actually using this. And that's, of course, if you're the only one in the world, it's not a good thing, a good space to be in, and certainly in the evolution. So how do we get out of there? So we had basically it's a distributed source of truth. It's tightly coupled. It's infrastructure-led. So basically our developers were not aware, it was also said, they are not aware where these things are running. Are we running in A? Are we running in B? Where are we running? So that was all led by infrastructure. And that made our developers, in a sense, complacent. So they didn't really understand all of this stuff and everything that comes with it.
Yeah, and if I may, what this helps us to do is actually it allowed us to avoid having a fractured state between different data stores, and it also helped us to, if one piece of data is lost, the most dangerous thing is that it's lost on one data store, but it's not lost like on the mainframe or the open system. So it really helped us to maintain that data consistency across those two worlds. If we were to lose data because of an incident, this will assure that this piece of data is lost in two places. Because the worst thing you could have in these cache databases reporting collateral is that some information is there, but some is not there, right? So yeah.
Yeah, maybe one thing that I wanted to say here is that if you can see it there, we actually at that time we prioritized, when we were in region, we were prioritizing availability, and we were out of region, so we are in the C part, we are prioritizing consistency. And that was something done in 2000, and I'll come back to that in a couple of slides.
So we needed to change, right? So we were at the mercy of the regulator, of course. They were not very happy with how we were doing things. Let's just keep it at that. We were in a state where we must adopt autonomous availability zones, autonomous data centers, autonomous region, be active in multiple places, right? And we were told that we must also be in a state where, if we were to have a prolonged outage or a prolonged planned swap, every major application needed to be there as well. At the same time, one key regulatory imperative, which makes sense, is how can we ensure that when we re-architect all of these things, we can limit those blast radiuses, And for us, a blast radius is not only from an availability perspective or a failure perspective, but it's also from a data consistency point of view, right? And also like a security point of view. But we were also at the mercy of our technical debt, right? So this whole thing that we showed you, which was purpose-built only for us, so we might be the only client or two clients in the world that were reliant on this technology, which made all of the application developers quote-unquote lazy, because they offloaded all of these non-functional requirements, data integrity, etc., through that ECG. So we needed to change, but what really happened is that the vendor that was providing us this technology announced a while back that they're gonna stop it, right? We had 3-4 years to get rid of it. So this is important. The other thing is that the regulator wanted us to provide evidence that we were gonna be able to auto-heal services and auto-swap, right? So this is very, very important. And this is not only for failures that are unplanned, but also for frequent plan tests, frequent planned zero downtime maintenance, application releases, etc. And we also have a much bigger, wider scope of applications and workload, right? So for us, the answer is that we must decouple this ECG, this whole one solution fits all, into more of like a modern way of doing things, right? And as everybody, we also have our own plans to adopt clouds the right way, right? For us, when we talk about cloud, it's cloud the right way. So yeah. So we looked at to do it. We started by creating something called the MVFMI, the Minimal Viable Financial Market Infrastructure. I know it's a big of a difficult thing to say, but it was a way for us to classify those mission-critical applications and make that problem small. So prioritize which application we wanted to start to develop and really focus on, right? And we also wanted to move away from this monolithic way of providing data replication and data consistency into more of a granular per application way, right? And of course, we started to influence our application developers to start to worry about resiliency, because for us, application needs to pull its own weight. You know, it needs to provide all of the non-functional requirements and really adopt modern reliability capabilities within the application itself, within the middleware, within the cube world, the streaming, etc. And then we wanted to really think of something that we were gonna build for the next 10, 15 years, right? So this idea that we should rely on autonomous AZs, because we wanted to make sure that we don't share fate in anything, right? As much as possible, of course. So we needed really to decouple a lot of our applications from the platform, from the infrastructure, etc., right? And while doing this, we also want to whenever we can, remediate any technical debt. And that's a big story by itself, but still, there are opportunities, there are ways for us to have some quick wins here and there, so this is important. And also, as a future-proof mechanism, is also to be aligned with whatever new regulatory mandate that we should be really aligned with, all right? Now, to achieve this in our world, we couldn't make it each team create their own things, you know, so we needed to create a way to be standardized set of deployment patterns, architectures that are in such a way that think once, apply many, right? So having a way for us to assess every single application and their dependencies, and then create a set of repeatable deployment patterns, you know, and also a set of repeatable transformation runbooks, you know. So we wanted the application owners and the developers to follow a set of, to some extent, complete changes, adaptation which we thought were important for us to achieve this goal, right? And again, we also at the same time forced or trying to force the application to move away from that all-in-one data consistency capability and make the application itself handle in a new framework things around how to deal with state. And all of this needed to be done one application at a time. So this is very important that, again, if I go back to the MVFMI, reduce the scope, because you cannot do all of this very quickly. You know, it's a gradual, slow process, but you need to provide proof and success stories so that everybody else in the organization are influenced to actually help you, right? So in terms of the focus of what we want to deep dive with you today is from a Euroclear perspective and our new world is how can we guarantee fault isolation? This is really, really important because again, we embrace failures, everything will fail, everything will break, right? So that's a given. But how do we do it in a way to prevent that a single component, a single application, a single library, a single service would avoid the set of cascading failures? Because the majority of our application are intertwined. You know, they exchange a lot of files, messages, so on and so forth. So this is very important. And the second thing is all about how do we guarantee that every message, because applications talk via MQs and event streams, etc. So how can we find a better way to ensure a strong level of data consistency, ensure a sense of atomic exactly once way of reading data. So for us, from basically a way to achieve this, and we used to do this in the past, now it's called cell-based architectures. We used to call it like a swim lane, right? So one of the principles that we are enforcing in Euroclear is to make sure that all of our application and services don't share anything. You know, again, this is very difficult to do and very expensive, but this is a need. Grouping our applications into cells. And by the way, a cell needs to have the application and its platform and its dependencies. This is very important. And the way we were able to design this is to follow that critical transactional path. Right? This was very, very important. Those cells needed to be distributed in multiple location scopes. And for us, this is what we call an availability zone or a DC or a region, because we have cloud regions, we have on-prem regions, we have multiple availability zones, right? So this is important. And one element that we enforced in the design is that once traffic enters a swim lane, it has to stick to the swim lane. If something happens during it should restart, right? This is a way for us to provide sanity towards the operation team to understand what the hell happened, right? So of course, this also means that all of your failures and whatever failures it is from a consistency perspective, availability, but also from a security point of view, it will hopefully be bounded by this cell, right? Now, of course, each cell has its own size, its own location. It depends on the application, so on and so forth. But the important part to also remember that this is something new, right? Because now that you adopt this multi-active way of hiding failures, because again, failures will always happen, right? We embrace them. It's to ensure that cells are aware of where they are, right? And this means that the application and needs to be aware that this request, this API call came from this cell. It came from this location. Spanning cells is a big no-no. We do it when we have to, but we try to really avoid it. And this should make our lifecycle management on managing those cells, releasing new features of the application much easier, because now we're able to really do these changes one cell at a time. Okay, so it's a way for us to not only limit that blast radius from a failure perspective, but also how do we maintain a state of A/B testing between cells, if you do it one cell at a time. So that's one of the most, let's say, critical architectural shifts which we're doing to address reliability at the moment.
Yes, and then we have to move to consistency, of course. So Here, what we didn't realize when we did this in the past, so we actually were implementing cap theorem. We kept the partition, so cap standing for consistency, availability, and partition. So the partition part was kept fixed. So you have this in two-phase commit, they talk about stable storage and so. So that's what we did. So now, how are we going to move from cap theorem to cap theorem times a lot? Well, you have two choices. Either you add latency, so you introduce a lock step, which we basically are already doing with another thing that I didn't explain, but we have a legacy, an HP tandem non-stop system still running, so we're actually doing that, a lock stepping. You move into reconciliation. And you move in reconciliation, you can do that in various ways. You can do that after the disaster, or you can do that while you are running. So every 5 minutes, you actually snapshot to the other bounded context, whatever that you want to connect, and you want to do that. Voila, that's basically it. So what are the trade-offs? Because I think we have to move a bit. So there is the complexity. So we are losing this global atomicity, which was easy for us. So it's making things much more complicated. We have to also explain to management, which is also a bit of a challenge, because we have auto swap on. So we are moving today, we still do, and we will keep that in the future. We are moving our data center every 6 weeks. So the whole production moves into the other data center, and we are doing that every 6 weeks. Of course, we are testing the regional disaster part, and that we want to keep. We also have something which is an auto swap. It means that people are not actually deciding when they want to swap the data center. We do it automatically, depending on the trigger that provokes it. So here on the trade-off, so we have something that was working, now we're adding complexity, loss of global atomicity. So what do we do with read stale data? So what do we do with that? So if we want to preserve consistency, can we ignore data? So that depends. So in the availability part, we have to ask the question, and then of course, does management understands all of this? Is going to be a complicated, and it is a complicated dialogue. So on the right-hand side, you see what we're going to do after. So we're going to decouple the red boxes. So you're going to, for example, in the example that we're going to give, is going to be settlement between cash. How do we make them sync them up? And maybe we can go to the next slide. The way that we want to do that is with outbox and inbox framework. So on the left-hand side in the drawing, you see settlement, so typically running on mainframe. We want to be aware that we have a bounded context. So the dashed stuff is really, so that means that we have, we have double writes, we have, all these caching issues. So the system doesn't lie. In a bounded context, the system doesn't lie. We are sure that we have the correct data. That's a given, let's say. It is not a guarantee, but it's a given. That's what we mean with a bounded context. And if you move to something else, an open systems, that they have their own bounded context. And how do you communicate? So between two bounded contexts, you have to have a communication which is precise. It needs to be very well defined. So you have an outbox an outbox table in our case here, which means that you're going to write the transaction in an atomic way into the business table, but also in the same database on the outbox table as well, so that you can actually see what a drift detection is. If you go to the other side, does the same thing, so it reads in an atomic way, and it will actually also understand that it's missing a transaction. So maybe you're going to the next slide. So if you look at it, what I was just saying, so for example, here is we are going to begin a transaction with an action A. We update the settlement table, then we do the write to do in the outbox table, and that is a commit. That's an atomic, classical two-phase commit stuff. And then we're going to, in step 2, the message is relayed. So it means that there is a background process that is watching the outbox table. It will actually propagate the message through the other bounded context environment, and it will also flag it as being sent by MQ because it confirms. MQ on our side is in the bounded context, it's persistent MQ. It's the same story as everything else. So it needs to be atomic. And then on the step 3, it's the receiving of the process, where basically it's again, reading this it reads the information and it sees, for example, that we are missing a transaction in this case because you detected drift, right? And so this is whatever happens underneath, the database does something weird or anything else, we cover with that.
Yeah, so I mean, the important part to really understand here is that we made every bounded context aware of what it is supposed to send and to whom. And if that message, because we're talking about billions, if that value was sent from his own side, and then we also created a way from an inbox perspective, so the receiver end to ensure that they have received in an atomic way this value. And and then we have a cron job every minute, every 5 minutes to ensure that these outbox and inbox tables are in sync. And if they're not, then something happens. Either you act automatically or you shout or so on and so forth. Right? So the way it works, I mean, we don't have time to go into how this really works, but what the most important part for us to really reflect on is that we're able to move away from strong linear data consistency into something I call eventual strong data consistency, which makes no sense. But it's a way for us to in the same database on each side to be aware of what was sent to the other database, and if those two things are adrift, then you can really react on it. So how do we get there? I mean, look, the tech is the easy part, right? From a reliability perspective, when we talk about shared fate, this is important. We need to map and really understand what are the components that are being shared, right? And try to really remove them, right? Now, there's also this idea that many people are trying to move us or trying to influence us to move into many cloud native microservices way, which we are doing a lot, by the way, but there are things that, have been proven to work, and there is no real reason to actually move into a cube way of doing things. So from our perspective, evaluating the real cause or the real reasons behind moving into an OpenShift or Kubernetes world for this application, is it really a need, or are we just like following a trend? And the final point for me, and I know that I only have a few minutes, but industrializing this is very important for our scale. We don't have time to let every application owner and every application team to come up with their own weird way of doing things. So it was very important for us to build a foundational way to architect properly, document, socialize as much as we can, and then have a way to certify a set of deployment patterns, agree on a set of standards, and make sure that in a CI/CD, and when you're able to, when it's time for you to deploy, you attest. Did you meet that L1 of changes, L2, L3, so on and so forth?
Okay, so we have less than a minute. So I think this last part is really important. So it's the culture and the unknown unknowns is actually more difficult than the technology here. It's as Haytham was saying. So everybody has to own the reliability. I think the second point is important. How do you transfer knowledge? This is about the sense giving and the sense reading or receiving, where everybody is coming from a different context. So if you have mainframe guys, they have this different context, culture, and experience. So we have difficulties with that. Things once and deploy many. So challenge yourself. We have a test bed. We already had the test bed for 20 years to test everything because we cannot test in production. So we did more than 100 swaps of production switches, but we do also many more tests in the test bed. We will eventually do house testing. That's not a guarantee. That's a bit tricky in our environment, but we're working on that. And then the last 2 points is really, so don't think New scenarios will always doubt your knowledge, and I look at it as a kaleidoscope. You think you understood this stuff, and then apparently something happens, and you said, "Whoa, Jesus, that was not. I didn't think about that." You should accept it, and you don't have any visibility on the failures that are coming towards you. Voila, that's it. And the last thing that we just included: cool readings of books. I think the first two, you know these. The third one is also something mentioned already a lot of times. I would recommend the fourth one, which is the Static Monoliths and the Microservices book. Is a very good book. I think you recommend that. And of course, we have the book from Haytham itself. We have to stop here. Thank you very much for
Thank you very much for having us.